So I'm going to begin with quite a long, very long introduction, and I'm going to begin by recapping the motivic fundamental group of P1 minus 3 points. I'm going to go fairly fast because I don't want to spend the whole talk on this. So this is a recap on x equals P1 minus 3 points. So we begin with a point, let's say a rational point for the sake of argument, and pi is going to be the fundamental group of the normal topological fundamental group of the complex points of x at the point x. And there is the unipotent or Maltsev completion, pi unipotent, which is an affine group scheme over Q, and its affine ring O of pi unipotent is defined as follows. It's the limit as n goes to infinity of the group ring of pi truncated by powers of the augmentation ideal and then dualized. So I should remind you that, of course, Q of pi is the group ring, and I is the augmentation ideal. So this is the map which sends an element to 1. Okay, so think of this as some sort of simplification, some sort of linearization of the fundamental group. So the next step is a small variant.
But that's not the ring. That's the code. You get the
This is a Hopf algebra. No, I'm taking dual. Sorry. Yeah, but it's actually the simplest way to present it. So you can define pi. You can take the projective limit without the dual, but then you have to take the group-like elements in that, and it's quicker to do it this way. So now take 2 points and assume that they're distinct. Again, for simplicity. There's again you can't take the group ring. It's not an algebra anymore, but the corresponding thing is a module over Q pi, where you choose, say, one base point here. You can look at the image of the augmentation ideal and complete in exactly the same way. And the upshot is that you get a version of this with 2 base points. So it's an affine scheme. And this time it forms a groupoid. So there's elements in, say, the Q points of this can be thought of as paths, and you can compose them in the way that you expect. Okay. So now the whole story begins by putting a sort of motivic structure on this, and I want to try to justify that. So a basic construction is to consider any path into the complex points of P1 minus 3 points. So a smooth path, for example. From this, you obtain a map from the n-fold product of the interval into the n-fold product of C minus 0, 1. And maybe I'll write it here. For future reference, let me define delta n contained in the unit n cube to be the simple x consisting of points which are strictly increasing between 0 and 1. So it's some sort of triangle in a square, something like this. And now the key observation, which is due to Bailinson and based on work of Wojtkowiak, although historically I think it came rather late in the story, is that the truncated group ring, well, actually not in this case I have 2 points, so this truncation is isomorphic to the homology of something, and that is the n-fold product of P1 minus 3 points relative to something. And the map takes a path from x to y and sends it to the homology class, the relative homology class of the image of this simple x in the space x to the n. So yn here is a union of, so this is contained in x to the n, of divisors, x cross x to the n minus 2, union dot dot dot, union x to the I minus 1, cross the diagonal, cross x to the n minus I, union dot dot dot, union x to the n minus 2, cross y. So this, in the case n equals 2, this y simply looks like a triangle. And if you think about it, the image of this simple x under any path has its boundary contained in yn of c, in the complex points of yn. Maybe I should put yn of c, to be more precise. And therefore, this defines a relative homology class. So that's the key, absolutely the key point is that this thing on the right-hand side is the homology of a diagram of algebraic varieties. So it carries lots of extra structures. So the right-hand side is the Betti realization of a mixed-state motive and a mixed-state motive is an iterated extension in a suitable category of Tate motives Q minus n and are integers, and I remind you that Q of minus 1 is H2 of P1. So this is kind of clear because x itself is just P1 minus some points, and the product of x is what it is, and y is built out of hyperplanes. So it's kind of clear that this cohomology is built out of the cohomology of projective spaces. So we expect such a thing to be an iterated extension of Tate motives. That's kind of clear. Okay, finally, so what that means then is that you can put a motivic structure on this thing at least, and by dualizing on this dual vector space, simply by defining the motivic fundamental group to be a limit of these homology groups. So x pi y motivic, this is the space of paths from the point x to y, is therefore defined to be the spec of the projective limit, sorry, the inductive limit of hn of x to the n relative to yn. So this is an ind object in some suitable category of motives. If you don't like the spec, just write O of the affine ring is just this inductive limit. So from this, you can now write x pi y and put a dot up here, and you simply, in this definition, you simply replace your dot with your favorite cohomology theory. So dot equals Betti, which is the previous case, or de Rham, or something else. And now the interesting case, the most interesting case, as Dick vaguely mentioned, briefly mentioned in the last talk, is when x, do we need a yet further degree of sophistication, unfortunately. You'd like to take, the natural choice of base points would be 0 and 1, but of course they're not in the space. So a construction due to Deligne is to take tangential base points, and you can take x to be the tangent vector at 1 and y to be the negative tangent vector at 1. Sorry, I said 1, I meant 0. So x is the unit tangent vector at the origin, and y is the negative unit tangent vector at 1. So it's quite easy to see that you can do a theory of topological fundamental group with respect to tangential base points. Just have paths that leave this point with the appropriate initial velocity and come back. The metric theory is considerably more tricky. But anyway, the upshot of this generalization is a series of bullet points. The first is that the affine ring of the metric fundamental group from x to y. So now, from now on, x is actually, so I will call this 0, and I will call this 1. Then that saves me a lot of hassle. So in this particular case, where the base points are 0 and 1, or these tangent vectors at 0 and 1, this thing is an ind object in sort of the technical category of mixed state motives over Z. So this is a theorem due to Deligne and Goncharov, which is much more general than this, but I'm only going to consider this. Now, unfortunately, there's some input that comes from this point of view that comes from outer space, and this is one of the major failings of this theory, is that you have to appeal to some different part of mathematics. And we know that this category of mixed state motives over Z is a Tannakian category, and it has a canonical fiber functor, and it is therefore equivalent to the category of representations of a group I'll call G de Rham. And so G de Rham, we know a few things about G de Rham. It's split as a semi-direct product of the multiplicative group with a pro-unipotent affine group scheme, U de Rham. So the Lie algebra of U de Rham is graded by the action of Gm. And the graded Lie algebra of the unipotent part is a free Lie algebra on generators that I'd like to call sigma 3, sigma 5, sigma 7, and so on, where sigma 2n plus 1 is in degree minus 2n minus 1. So this is a result that comes from Borel's very deep results on algebraic K-theory. And it's important to bear in mind that these elements are absolutely not canonical. A priori, they're not canonical. And we don't know very much about them, frankly. So we have an object in some Tannakian category. We know the Tanaka group, more or less. And we know its structure, at least. And one implies that the de Rham realization of O0 pi 1 is a representation of G de Rham. So G de Rham acts on O0 pi 1 de Rham, and we know that it acts faithfully. And the upshot of this, as Dick mentioned, is that in fact this object constructs for us every object in the category MTZ. It generates MTZ. Okay, we start off with a specific example, and at the end we find that we've actually constructed everything. A quick word of how you do this. I'll say be extremely brief because I want to generalize this a bit later. We have, we know that GDRAM acts on this. Another way to say it is, in fact, UDRAM, we can restrict the action to UDRAM, acts on something. It acts on the DRAM fundamental group. And so therefore it gives a map to the automorphisms of this, whatever this means. And so now it gets a bit technical. You have to consider the right automorphism group, which is in fact the automorphism group of the collection of all these DRAM fundamental groups. For x, y in these set of two tangential base points. And then you need to know some constraints about the image and try to compute something. And the more information you know about this automorphism group, the more you know about the image of UDRAM inside it. And if you're lucky, you can take one of these elements, which is not well defined, and try to compute what it looks like here. And the more information you have about it, the more happy you are. And then you can try to prove that they form the image is a free thing inside here. So I'll just mention that briefly because that's the scheme I want to follow in the case of SL2. So briefly, what are the periods? Periods obtained by pairing Betty and the DRAM realizations. And the upshot is that you get regularized iterated integrals of the only two differential forms you have on P1, P1 minus 2 points, which are defined over Q, along a path from 1, 0 to minus 1, 1. And there's a canonical such path, just go in a straight line. And if you work it out, the answer is that you look at integrals over this simple x, delta n, of 1 forms dtn epsilon n minus tn, where epsilon I are in 0, 1. These integrals diverge. That's why I put the word regularized. But you can regularize them in a certain sense. And the upshot is that they always give linear combinations of multiple zeta values, which are numbers defined by Euler by the following nested sums. And here I assume that nr is greater than or equal to 2 for convergence. And the philosophy is sort of that everything that goes on motivically is reflected in these numbers. So I should perhaps say it's tempting to think that we have this complicated motivic thing, which is all algebraic geometry, and the periods is just something you take at the end as an afterthought. But that's not how it works. In fact, the only way that I know of to understand the very intricate arithmetic structure of this fundamental group is by reading the information off relations between numbers. And even a p-adic period won't do the job. So the periods are really, really fundamental to understanding the structure. Okay. So now, Deligne, a few years ago, maybe many years ago, I'm not sure, did a similar story. So by similar story, I mean, so the bullet points 1 and 2 here are 1 is true in very great generality. Take P1 minus any rational points or something like this. 2, we have a category of mixed state motives over any rings of integers in number fields due to the work of many authors. But the real headache is part 3. So Deline managed to prove the faithfulness for a different setting, P1 minus 0, the group of nth roots of unity and infinity. In the exceptional cases, n equals 2, 3, 4, 6, and 8. And it generates, the motivic fundamental group generates something. It generates the category of mixed state motives of the ring of integers of Q adjoined a primitive nth root of unity, inverted n, in the case n not equal to 6. In the case n equals 6, it's something slightly different. So that's the philosophy works in this case, for sure. But then it gets a bit worse because Goncharov has shown that, in fact, the part 3 is false for certainly n a prime number greater than equal to 11. That means that the motivic fundamental group of these spaces, where you take roots of unity, does not generate the corresponding category of mixed state motives in those cases. So I apologize, this is a slightly straw man argument, but this suggests to me that this whole story has flaws. And one such flaw is that there is no conjectural prescription, for example, for constructing the mixed state motives over Q. The problem here is that we want to invert primes and we end up going into larger number fields. So you could try to remove more points and do a Galois descent argument, and that turns out to be much more difficult than you think. So I have a PhD student working on this. It's very tricky indeed. So we don't really know what to do at this point. Another criticism of P1 minus 3 points is this one here, is that there's nothing about P1 minus 3 points that tells you that you should have this Lie algebra with one generator in every odd degree. This comes from a different part of mathematics. And that's very unsatisfactory. Another way to say it is that the natural thing of P1 minus 3 points are these numbers, and a priori there are 2 to the n of them in degree n. But because we know the structure of mixed state motives, the answer is actually the size of the enveloping algebra of that Lie algebra, which is approximately 4/3 to the n. So it says that P1 minus 3 points is far too complicated. It contains far too many numbers, and they must have lots and lots of very complicated relations, which we don't understand. And it's somehow too complicated. So the program that suggests itself is to change the geometry completely and replace P1 minus 3 points, the unipotent completion, multiple zeta values, and mixed state motives over Z with, instead of going up into moduli space of higher genus, one can look at quotients of the upper half plane by finite index subgroups of SL2Z. So I don't necessarily assume they're congruent subgroups for now. The unipotent completion will be replaced with the relative completion, which we heard a lot about just earlier. And multiple zeta values will be replaced with something I like to call MMVs, multiple modular values. And MTZ, well, here we have to pay a heavy price. There should be a category of mixed modular motives. I have no idea what such a thing should be. But we want to construct lots of examples of such objects. And we should bear in mind, of course, that when P1 minus 3 points was done, that the category MTZ didn't exist at the time. So I'm perfectly happy with working with realizations. A remark due to a corollary of Bélié's theorem is that MMM, this should be extraordinarily rich because it should contain not only the motives of all modular forms, but in particular the H1 of all algebraic curves defined over number fields. And so the strategy then is to study MMM via its action on. So let's imagine some category with this time it'll be a Betti fiber functor, and it will act upon relative completion, because it will be some object in this, a Betti realization of an object in this category, we hope. And so we get a map from pi1 MMM, whatever that is, into a certain group of automorphisms. Well, let me put gamma here. Let me just put nothing. A certain group of automorphisms, more on that later. And again, you want to try to understand constraints on these automorphisms group. And the goal is to look for interesting elements in this group that will tell us about this category. So in particular, so if this map were injective, by which I have no idea, then it would mean that we could construct all the objects from iterated integrals of modular forms. So the question is, do mixed motives of a certain type come from modular forms? Well, so you have the Bayesian conjectures, and you know that the generators of the binalization of the Lie algebra of this should correspond to L values of modular forms and possibly rank in Selberg convolution. So I'll come to that later. We can exhibit something, but so I can construct things here that shows that it's quite rich, but I have no idea whether this whole thing is injective or not. I'm not so bold as to make a conjecture on those lines, but we'll see that later. So MMM in particular should contain MTQ. That's so much I do think I believe. And if that's true, that would imply a modular construction of MTQ. So I'd like to call this the modularity of mixed state motives. And I'm only going to look at the case of SL2Z today. And so we hope to construct mixed state motives over Z from SL2Z. And what we find with SL2Z, so this is what drew me into this in the first place, is that we know we have Eisenstein series, E4, E6, E8, and so on. And as I will try to explain, these Eisenstein series in degree 2n plus 2 corresponds to these elements sigma 2n plus 1. So whereas in P1 minus 3 points there was no geometric source for this structure at all, for SL2 the geometric structure is staring us in the face. We naturally see a copy of the correct Galois group already there. So that's why I think it's more promising. Okay, so now after those preliminaries, I want to just focus on some aspects of this. And I'll start off with what is probably the most popular and certainly the most elementary, which are the periods. And then I'll try to say something about automorphisms. Well, we don't understand the action of Heck operators yet. So no, so if this Bélier results, of course, uses non-congruence groups. I mean, otherwise, so if we want to, we should make the box as big as possible for now. But we don't understand how the Heck operator is what they're going to do on these iterated extensions. It's not clear yet. Yeah, sure.
Like for any group?
Yeah, for any gamma, so you could put each group gamma will generate some subcategory gamma. So the hope would be, okay, well this is all very conjectural, but the hope would be you to look at congruent subgroups, and if you count, so it's a back of an envelope calculation, if you count the number of different Eisenstein series and you look at their periods, it seems to match up with the algebraic K theory of the corresponding cyclotomic field. But I don't know whether this is very far off. MTQ would be contained in some union of MMM gamma, gamma naught n, something like that. You're pushing. No, Bailey's theorem is just a philosophical thing. It's because I read Grondix's Kister program, and he gets very excited about it. It's just to say that it's a big box, and we shouldn't worry that this is specific. No, in practice, of course, it's hopeless. You can't use Bailey's theorem. Okay, so now I'm going to do something concrete at last. So multiple modular values for SL2Z. And I hope this will be very elementary. So MK is going to be the Q vector space of weight K modular forms for SL2Z. And they have a Fourier expansion, ANF Q to the N, and the coefficients will be in Q, for now at least. So that's a Q vector space. And modular forms are decomposed into cusp forms and Eisenstein series. And let me remind you that the Eisenstein series of weight 2K has the following Fourier expansion. P2K is a Bernoulli number plus some divisor function and they exist for all even, for all k greater than or equal to 2. And now I'm going to let Vn be the direct sum x to the I, y to the j, q, where I plus j equals n. So it's just a space of homogeneous polynomials of degree n. And just to be different from previous talk, it's going to have a right action. This is actually because the whole of the modular forms literature uses a right action. But we can switch, of course. And so it's denoted commonly by a slash gamma equals, so the action of a gamma on the pair xy is this thing, where gamma is the matrix ABCD. And for a modular form, any modular form in MK, I want to denote by F underline tor to be 2 pi I to the k minus 1 f of tor x minus tor y to the k minus 2 d tor. And we think of this as a section of the upper half plane in tensor v k minus 2. And then we need some sort of residue at infinity. So f infinity tor is 2 pi I to the k minus 1 a naught of f, which is just a number, times the same thing. And I want to view this as a section on C this time. And the reason is because I want to think of C as the tangent space at infinity of the upper half plane. But we don't need to go into that. So the idea is to do work out. So this is really an exercise. What I'm going to say, compute work out the theory of Deline's tangential base points, but on the upper half plane H, so on the universal covering of the modular curve. It turns out to be much simpler to do that than to work on the curve. So first of all, a reminder of classical periods, which were first studied, I believe, by Eichler and Schimmerer. As a warm-up, so F, a cusp form, you can consider the integral from 0 to I infinity along a geodesic, along a straight line, straight vertical line, of F underline tau. And the result is that this is a generating series of special values of L functions of the corresponding modular form. X to the n minus, sorry, k minus n minus 1, y to the k minus 1. So here's a picture of the critical strip of the modular form. This is a point k. It has a symmetry. And we only see the special values inside, strictly inside the critical strip. That's very important. So these are periods of pure motives. Another remark that Mannion showed, that when F is a Hecke eigenvalue, Hecke eigenform, so it won't be over Q anymore, but you can certainly write down the same integral, then this quantity here is just of the following shape, where omega f plus or minus are real numbers and p f plus or minus are polynomials with coefficients in the number field generated by the Fourier coefficients of f. So this is quite surprising the first time you see it. It means that a priori we have k minus 1 different possible numbers here. But in reality, there are only two, up to rational multiples or algebraic multiples of each other. They satisfy lots of relations, and there are only two independent numbers that pop out. And what I'm going to say generalizes this fact to all higher iterated integrals. So now, what about for Eisenstein series? Well, then this integral is going to diverge in this case. So you have to regularize it somehow. This was first done by Zagier, I think. Possibly Ramanujan knew this. And you get some multiple times the Riemann zeta value, x to the k minus 2 minus y to the 2k minus 2. Plus some power of pi, and then something which is rational. So this is some polynomial you can write down explicitly, but the key point is that it's rational. But we see a single Riemann zeta value appearing. Okay, so that's what was known certainly over 50 years ago. And of course, it is curious. Here we only get periods of pure motives, but the iterated integral of an Einstein series gives a period of a non-trivial extension. It's curious. So now I want to discuss the iterated periods. So let me remind you that if we have any manifold and one forms omega 1 up to omega n, smooth one forms on M, and we take a path 0, 1 to M, smooth path, then the iterated integral of these one forms along a path, so I will denote it with bar notation so as not to get cluttered with tensor products. So think of this is just the tensor product of the forms, if you like. It's just a notation. It should be multilinear in each argument. This is the integral over the same simplex we had before of the pullback of each differential form. So this definition is due to Chen and Dyson independently. And so Manning has considered the case where omega I are cusp forms. He calls them iterated Shimura integrals. But I want to explain how to deal with the Eisenstein series, because that's the thing that's going to correspond to the mixed Tate part of this story. I'm going to explain exactly how to regularize. Actually, since I did this, I got messages from about 6 different people saying that they had also regularized iterated integrals. But you have to do it the right way. You have to use the tangential base points. Otherwise, we're not talking about period. So the way that this regularization was done by Zagier was to, where is it? To replace K with S and do a sort of Mellin thing. And that's not algebraic geometry. So it works great, but and I think it gives the same answer. But we have to use the tangential base points. Anyway, I'm not going to explain how to do that. I'm just going to give the final answer because it's very elementary, and it could have been done 100 years ago. So I define a regularization operator R on a tensor of these modular things where the Fi's can be any modular forms, not just cusp forms now. And this is just the sum with some sign of F1 tor slash F tor up to I. You take the first I of them, and then this is a shuffle product. And now you take the residues at infinity in reverse order. I plus 1 infinity tor. So that's some linear operator on tensor algebra generated by differential forms. And then the regularized iterated integral from a point tor in the upper half plane to the tangent vector, the unit tangent vector at the cusp of an arbitrary sequence of modular forms equals sum I equals 0 to n, integral from tor to I infinity of the regularization of the batch of the first I times the integral from tor to 0. This looks very strange the first time you see it. Of the remaining forms with an infinity. Fn infinity tor. I apologize, I've run out of board space. So then the point is about this is that this is the definition of the regularized iterated integral. This thing converges exponentially fast, like a cusp form would. And this thing is just a polynomial. F infinity just involves Bernoulli numbers at most. So this is just a completely explicit polynomial in tor. So you can compute these to your heart's content. Unlike multiple zeta values where the convergence is terrible, in the modular situation we get exponentially fast convergence of these periods. So I hope that these will have applications in different subjects such as physics and so on. Yeah, so these are polynomials. I keep them separate for now. Yeah, can I answer that question in 1 minute? I'll just say something first. So then the natural thing to do is to form the generating series. I tor infinity equals the sum over all indices AFI1, AFIN of these iterated integrals. Where the AFIs are just non-commuting symbols. They're just placeholders. So in answer to your question, this will be this will be some function of Tor taking values in v 2i1 minus 1 tensor v 2in minus 2. Sorry. So, and a tensor product of polynomials in one variable can be thought of as a polynomial in several variables. So two modular forms say you get a huge number of periods, you get a polynomial whose coefficients are all periods. And so now the point is that for all gamma in SL2Z, there exists a formal power series C index gamma in the commutative form, the ring of non-commutative formal power series generated by these symbols and x to the I y to the j, where the multiplication on x and y is, as non-commutative variables, not as commutative variables. So I've got 15 minutes, good. And then so it's easy to show that this generating series of periods is a one cocycle. In other words, that CGH equals CG slash H CH for all elements in the group. That follows from the gamma invariance of this differential form. Okay, so we get some relations between the generating series of these integrals, these numbers. And a priori we get, for every element in the group, we get different periods. But because of the cocycle relation and the fact that gamma is generated by S and T, where S is the matrix 0, 1, minus 1, 0, sorry, minus 1, and T is the matrix 1, 1, 0, 1, then this cocycle equation here implies that this canonical cocycle is entirely determined by its value on S and its value on T. Now, its value on T turns out to be something you can compute completely explicitly, and its coefficients are in Q adjoined 2 pi I. And so I know this exactly. So all the interesting information is contained in a single formal power series CS, and CS should be thought of as the modular analog of the Drinfeld associator. So after all that, I can now define multiple modular values. The ring of multiple modular values for this group, SL2Z, is simply the Q algebra, or the Q vector space is equivalent, generated by the coefficients of the canonical cocycle evaluated on S. And if you just read off the coefficients in length 1, you get exactly this Zagier classical period integral, and you get the Eichler-Schimmerer one, which I've erased, unfortunately. So this is a generalization of something very classical. Okay, so now I want to say something about the automorphisms. So the way I like to think about these numbers is as possessing, or conjecturally at least, possessing an action of a motivic Galois group. So the next goal was to understand how they transform under such a group action. And that's precisely it's the next section but one. So what I've done so far in this is I've just computed just the iterated integrals of two Eisenstein series. This looks extremely, it's a very modest part of the picture, but as we'll see, it gives a lot of arithmetic information. So this is the regularized iterated integral of two Eisenstein series, and it's a polynomial in 4 variables. So if you prefer, it's an element in V 2m minus 2 tensor V 2n minus 2 tensor C. And what you find is that a lot of the coefficients are multiple zeta values of depths 2, 3, and 4. That probably doesn't say much to anybody, but for me it's absolutely crucial because it says that the SL2 is doing correctly what P1 minus 3 points doesn't do correctly. And this is connected to some important conjectures about the depth filtration. Then another example of numbers coming up in this, using a method of Harberland ideas, Utah-Passel and Popper, and a variant of the Rankin-Selberg method, you find that we also get the L values of all modular forms at the point n, where now n is outside the critical strip. So this is the W is the weight of F. So before we only had the L values strictly inside the critical strip, which are periods of pure motives. When you look at double Eisenstein integrals, you find the L values, special values of L functions, everywhere to the right of the critical strip. And the key remark for this is that, I mean, how do you do Rankin-Selberg to an iterated integral? Well, the answer is that you only have 2, yeah. So the point is that you have that an indefinite integral of an Eisenstein series is something we don't understand. It's not modular. But if you take its real part, it's a real analytic Eisenstein series. Then you can apply the method. Okay. So it means only 2. Absolutely, it means only 2. Absolutely. But it's some generalization. I mean, yeah. I could talk a lot about this, but sorry. Well, that would be very interesting to know. So, what I haven't, one expects to get the Rankin-Selberg convolution LF tensor G in an iterated integral of Eisenstein and Cust form, and that's very important because Beilinsen's conjecture is not known, I believe, for such an L value. So this would be very significant, but I haven't got around to that. Okay, so now G gamma is the relative completion. My concluding remarks. So, of the map from SL2Z into SL2Q, and so it's the largest possible extension of SL2 by a pro-unipotent group, and let U MMM be the unipotent radical of pi 1 MMM. I'm going to go back to again. I don't know what this means, but it's just a mnemonic to keep track of what we're doing. So what should happen if such a category existed? Then U MMM will act on this relative completion, and it will respect the map to SL2, and it will also fix, so this is a very stupid condition, it's going to fix the image of the relative completion of G gamma infinity in gamma. That means it fixes the monodromy at infinity. Gamma infinity is the subgroup spanned by -1 and t. Another way to think about it is that this co-cycle CT has only 2 pi i's in them, and they're going to be acted upon trivially by the unipotent radical. I would love to add more conditions, such as Haynes mixed Hodge structure on OG gamma at this base point. I would love to add, we could add the map to the Eisenstein quotient, and we could add, hopefully, Hecker operators and so on and so forth. But for now, all I did was just look at the most obvious conditions and try to see what information that gives us about periods and the Galois action. And I'll just finish off in a minute. So I haven't put any input in about the mixed Hodge structure yet, and it's quite surprising that you get a lot of information out. So now we want to study the automorphisms of the relative completion that respect the map, respect this map pi. And you can show that by this variant of Levy's theorem, a little bit of work, there's a non-canonical isomorphism of this to U gamma, semi-direct, the S invariant of U gamma, aut U gamma, SL2 invariance. The non-canonical isomorphism. And inside this very general automorphism group, I want to look at the subgroup satisfying 2. Ultimately, I want to add more and more information. But for now, I've just put this information in. So what that translates as, if I denote elements in here by B, comma, phi, so phi is an automorphism of this group to itself, and B is just an element. It boils down to what appears to be a very stupid condition, B slash T phi kappa B inverse equals kappa, where kappa is some element in U which I don't know. But I do know that in some sense, that I won't have time to explain, it corresponds precisely to this T cocycle, which I've completely computed. So this completely innocuous looking equation actually contains an infinite number of constraints coming from the monodromy around the cusp of iterated integrals of modular forms. So from the previous talk, we know that the Lie algebra of the unipotent completion is isomorphic to the completed free Lie algebra on H1 SL2Z V2N dual tensored with V2N. Maybe I should put direct sum. And so the automorphisms of this group should be things that the phi should be something which takes an element of H1 SL2 V2N and moves it to a Lie bracket as the same thing. This is very concrete. And so the conclusion is we get a map from the Lie algebra from UMM, whatever that is. We don't know what this is. But here on the right-hand side, we can construct some sort of quotient of this automorphism group. And we get the Lie algebra of U gamma Vn, which is completely explicit. And by truncating automorphisms to a certain degree, we get a map from this to wedge to the U gamma. Okay, so kappa is the image of T. We have so gamma infinity goes to G gamma infinity. It's risky dense. Goes to G gamma, and implicitly I've chosen the splitting. And then here the element T maps to kappa, comma T. So I don't know it explicitly, but I know its image in the holomorphic part. So now at the very final sentence, we can then sort of forage around for elements in this which should correspond to something here. So in here we expect to see something corresponding to these mixed state generators, and they correspond to seeing a zeta values a period. And by using just this stupid fixed point equation, you get a wealth of information about what you can get on the right-hand side. So I get an Eisenstein series times y to the 2n. And here I get a map from Eisenstein forms. So this was E plus C in the previous talk. Eisenstein and cusp forms to wedge products of the same. So the map here maps to some strange number, E2 n plus 2 wedge E2k plus 2n tensor V 2k minus 2. So this is a copy viewed inside 2n tensor 2k plus 2n minus 2. And we get new elements. This partially answers Patrick's question. We can see them. So these are going to correspond to the special values of L functions, or extensions of Q by the motive of a modular form. And here we get 0, and we get corresponding cuspal generator, I'll denote by AF. Here, weight of F minus 2 maps to some Fn AB. So I apologize for this formula, complicated. But it contains a huge amount of information. So let me explain. This piece here exactly corresponds to, it says that there's a non-trivial action of this element on the iterated integral of a single Eisenstein series. So it tells us there's a zeta value, and it tells us exactly where it occurs in this classical period integral. So it explains why we get a zeta value. This 0 here is exactly Manning's theorem, where we found that there are only two periods of there are only two numbers that could, with the space of values of the L function inside the critical strip only had two numbers. There was no extra component as we see in the Eisenstein case. This thing, if I restrict it to the Eisenstein quotient that Hein defined, gives exactly the action of the Galois group on UIs, which is one of his questions. And this is exactly equivalent to his cut product calculation that he mentioned at the end of his talk. And so this is some sort of prescription. It tells you if you want to construct an iterated extension of mixed state motives, then I apply this element to itself, and it tells me exactly which iterated integral of, in this case, Eisenstein series to find my extension, and likewise with these. So what I don't know is that there's an infinite sequence of other generators, nor what their images look like. I'll stop there.